Hello, everyone, and welcome to the second webinar of the series, So You Think You're Green. Maybe we'll wait another couple minutes or so, but just to give you a quick introduction. For the next hour, my colleagues Hilary, Melanie, and I will go through the various questions you may have about the environmental impacts we cause through housing and how we can make things better. So thank you so much for having registered and being here tonight, for having connected. For your information, it's going to be a 1-hour presentation with live polls to stimulate a bit interactions. If you have questions, there's going to be a session at the end where we will answer all of them, which means you can already write the questions in the question section of the webinar, of the page. So there's no need to wait for the end. You can already type even now. This will be a recorded webinar. So the video and the PowerPoint, the slides, are going to be available afterwards. And finally, there's going to be a satisfaction survey that will be sent out that we would really appreciate for you to complete. Okay, we can probably start. Check. Can control the screen. Everything's fine. I hope I can. Yes. All right. So before we start, I'd like to introduce our group and say a few things about who we are. The Luxembourg Institute of Science Technology LIST is a research and technology organization which focuses on 3 main topics: materials, information technology, and environment. Within the latter, the Lifecycle Assessment Group works with evaluating the environmental impacts of technological solutions, products, services, but also decisions, policies. So we work mostly with private company and public organizations. So we have a broad range of activities. But first, second guess, we will have a poll to ask you a very easy question to answer. So poll, please. So the question is very simple. We would like to know if you have already participated to the previous event on mobility. You can't go wrong on this one. Just click yes or no. It's for us to know how we should shape the rest of the presentation, if we should refer a lot or not to the previous session. So I guess we're almost good. Maybe 5-10 more seconds. Okay. That's really good. So we have a lot of first comers tonight. So 29% have already seen the first presentation on mobility and 71 haven't. So for the 71%, you can always go back and watch the first video later if you want to. I'll pass the next slide, please. Yeah, thank you. But don't worry. So I would like the 71% not to worry, because I will explain first in the first section the concept of carbon footprint and how housing actually contributes to that. So let's start big. This is a graph of the world's CO2 emissions from 1870 accumulated on the x-axis here. So basically you see that today we have emitted a little more than 2,000 gigatons or trillion tons, trillion tons of CO2 since we started emitting CO2 from mostly fossil fuels. And on the y-axis, you can see the observed and modeled warming of the atmosphere. And we're at about 1.3 degrees of warming, which is quite high. But most importantly, you have to remember that this is a global average, and actually warming is stronger on land than on the sea. So the average on land today is about actually 1.9 degrees since we started emitting CO2. So if we do nothing, we might reach 4.5 degrees of warming at the end of the century. At more than 4 degrees Celsius, very significant consequences occur. More frequent and intense climatic events, for example, storms, sea rising, which will also displace probably at least hundreds of millions of people living on shores and deltas, Parts of the world will also not even be inhabitable for a certain time in the year. They will reach temperatures at which you cannot even physically sweat to regulate your body temperature. So we don't really want to go up there. So with moderate measures, it's estimated that we could plateau at 3 degrees Celsius, but with extreme efforts, it's probably something you're most familiar with, is this 2-degree target that has been enshrined in the Paris Agreement. So in this agreement says that we will try to stay well under, that's the term, 2 degrees, which means that if you translate that in CO2 or greenhouse gases left to emit, you only have a wiggle room of 800 to 1,000 gigatons that's left to emit for humanity forever, after which we have to stop completely. So it seems a bit remote, both in terms of space and time, I guess. So we'll try to make it more relevant to us. One first thing we have to remember is that now we mostly mention CO2, which we emit about 40 gigatons per year. But it's not the only greenhouse gas. Other substances have the ability to warm the atmosphere. For example, fluorinated gases, mostly used in refrigeration, are very powerful greenhouse gases. They are used for their high ability to carry heat, but if they leak in the air, they are still as powerful in the atmosphere than in the fridge. So we don't want them in the atmosphere. Then come dinitrogen monoxide, N2O, and methane. So they also have global warming potentials. If you want the numbers, they are here. But the two last ones we'll probably talk about more in the next session on food. Let's focus back on CO2. So CO2 emissions have various origins. First, land use change with about 10%, I think, of emissions. Then process emissions from the industry, notably cement. And then the infamous trio of fossil fuels. So there's coal, gas, and oil that actually represent the overwhelming majority of our CO2 emissions. But now we do not really consume these things. I don't have coal, or I have a bit of gas probably at home and a bit of fuel in my car, but most of these energy carriers we don't use directly for our services, for eating or for food. So all of that will actually be consumed through first a refining of fuels that will be used in machines, devices, factories, and everything that really makes the products and the services that we use in the end. So some equipment, for example, at this stage, which you can also gather in sectors, which what matters for us as consumers is the service. And today we're going to talk about mostly this warmth part and the construction part here. So last time we talked about mobility. And once again, we can even bring this back to the personal level with the idea of carbon footprint. But before we get there, there's another question for you, and I would like you to answer. If we have the poll question, please. Yes. So how much does housing contribute to the carbon footprint of an average Luxembourg resident? So you may have an idea of how much carbon you emit over a year, and a share of that is actually from just living at your place and a bit having built the place. So is it 8%, 15%, 24%, or 39%? Maybe 5-10 seconds more, and then I'll give you the answer. Are we good? Excellent. We'll see. Okay, so most of you have answered 24%. That's quite a good guess. And then it's mostly around 27 and 16%. Only 8% have answered 3%. Can we go back to the slides, please? Great, so let's see right away. what happens? So transport comes first, actually, in your carbon footprint, and then the right answer was 24% because housing comes next. So congratulations to more than half of you who guessed it correctly. And then, of course, come other things such as consumption goods, food that we will address in the next session, and public services, for a total of 14.5 tons per person per year. So to those who are here in the first session, you may have noticed that we're showing a bit different numbers. It's because we have recalculated the footprint with Luxembourg specific data, which was not the case originally. So this is more precise. All right. So for today, yes, I forgot to say, we have to put all these boxes in the 2-ton budget box by 2050. It's going to be a huge challenge. We have already addressed some solutions for the mobility sector, but mostly today we'll talk about how you can do something at your scale at home to actually reduce this housing share and try to get into that box, or at least on the way towards a 2-ton budget. So the outline for today, talked about carbon footprint. Next, Eloy will tell us about your house carbon profile. So why is housing so carbon intensive? And then we're going to talk about heating and electricity separately. And finally, the house design will be presented by Melanie, with some conclusions and takeaway messages at the end. So I will leave the floor to Eloy.
Well, thank you, Thomas, for this introduction. And now we will go deeper into the topic of today, which is the impact of our house. So why our house emits so many greenhouse gases? To illustrate this, I will show you the results of a study from the Research Center of the European Commission, who calculated the carbon footprint for housing for an average European citizen. So it's the same unit that Thomas used for the Luxembourgish carbon footprint. Here it's in kilogram of CO2 equivalent per person for 1 year. So before you live in the house, you need to build the house. And for that, you need some construction materials like cement, wood, glass, etc. And of course, you need different processes to produce these materials, to transform the raw materials in the nature to the final construction products. All of this process will require some energy that partly rely on fossil fuels like oil, gas, and coal. So when we burn this energy, we will emit CO2 emissions. We will also have some CO2 emission due to chemical reaction for the cement industry, as Thomas mentioned it. There are also indirect greenhouse gas emission because we are producing chemicals to treat the wood, for example, or there are also transport activities. Then, once you have the construction materials, you can build your house. And for that, you need some machines that will consume, for example, diesel, that will emit, again, CO2. So you can see that this red bar here is much smaller than the blue bar, because you can imagine that the machine for construction use much less energy than, for example, a blast furnace that will melt steel. So once your house is built, you can live in your house. And during this period, you will consume energy and water. Some of the greenhouse gases will be almost visible in winter because we have this smoke going out of our chimneys. And in this smoke, we have some CO2 because maybe we are burning wood or gas to heat our house. We'll also use electricity that is partly produced on fossil fuels, therefore generating greenhouse gases. To have water, we need also to pump the water, to treat it and distribute it until our tap. So this also emits greenhouse gases indirectly. So this green bar is very large here, and we will see why a bit later. Once you are still living in your house, maybe you want to do some works. So changing the door, isolate your roof, and so on. And for that, you need, again, some energy and materials which will emit greenhouse gases for their production. So this bar here is quite small. And finally, you can demolish the house. So for that, you need some machines. Some of the waste will go to landfill, some other will be valorized energetically in an incinerator, or some other waste will be recycled. And you see this light blue bar here is negative. So how can we have negative greenhouse gases? In fact, the Commission considers here that when we are recycling waste, we are avoiding the equivalent production of virgin materials. and there is quite a large proportion of demolition waste that can be recycled, like steel. Therefore, the benefits are higher than the impacts due to the demolition or to the landfill of the waste. So to have a first explanation on the length of the green bar here I give you some temporal consideration. So you built your house once, it takes a few years, but then you will use it for between 50 to 100 years. So it's a very long time period in which you will consume a lot of energy and water. This is why it's so large here. So now we will open a new live poll to test a bit your knowledge. And we will try to understand in Luxembourg, what are the top main contributors to the energy and water use impacts? So the green bar. Is it first the use of electric appliance? So the fact that you are consuming electricity via the use of your fridge, the TV, the dishwasher, and so on. Then the heating, and then the hot water. The second proposition is first the heating, then the electric appliance, then the hot water. And the third proposition is first the heating, then the hot water, then the electric appliance. So I will give you a bit of time to think about it and understand what are the main contributors. So again, just to say that the electric appliance, they involve a lot of different types of equipment. The washing machine, the electricity for your smartphone, the TV, your Wi-Fi system, etc. The heating that you will use for the winter period, and the hot water is because you don't want to take a cold shower or to wash your dishes with cold water, so you will hot your water before to have a hot water. Okay. So if you don't know, of course, just try. And when we are ready, we can show the results. Okay, so most of you think is first the use of heating, then hot water, then electric appliance. Good, so let's see what is the correct answer. We'll go back to the presentation. Yes. So the correct answer is first the heating, then the electric appliance, then the hot water. So it was the second proposition. And before we detail this, I wanted to show you how much energy and water we use in Luxembourg. So on average, an household, a person in Luxembourg, we consume almost 10,000 kilowatt-hour per person per year. This is about 50% more than the European average, and we will consume about 150 cubic meters of water per year. So in terms of carbon footprint, we have first the use of heating, so it generates about 2,200 kilograms of CO2 equivalent per person per year. Then the use of electric appliance is about 400 kilograms of CO2 equivalent. Then the hot water, and then some minor contribution for the supply of water, the lighting, and the use of cooking appliance. So in total, we obtain 3.1 tons of CO2 equivalent per person in Luxembourg just for the energy and water use, which compared to 2.3 tons for the European average. So we really need to decrease this impact in Luxembourg. And for that, the priority is to reduce these heating impacts that contributes to 64% of this green bar. And this is what we will speak about now, the heating impacts. And we will try to understand what influences the impacts of heating. So I will show you now an equation, but don't worry, it will be easy to understand, I hope. If not, just ask a question. So we have a first factor here that we call the energy intensity. So how much energy in kilowatt hour we use per square meter of our house for the year. Then if we multiply this by the size of our house in square meter, we obtain the energy used for the year. So you can check this also with your bill. You can again multiply this by the energy impact in kilogram of CO2 equivalent per kilowatt hour. You will obtain the carbon footprint of your house for 1 year. And to have your individual carbon footprint, you can divide this by the number of persons in your house. So let's speak first about the energy intensity. This is influenced by the temperature, and in particular, the difference between the temperature outside and the temperature you want to set inside. And here we have a great role to play. And we need, of course, to minimize the heating temperature inside to minimize the energy intensity. So it's recommended to set a temperature of 19 degrees in the room you are using and to put a much lower temperature in the room you are not using, like 12 or 13 degrees. But it's also influenced by the performance of your house. So the ability of your house to keep the heat inside. And this is influenced by the different types of house. So we have made a study for the city of Esch-Alzette, and we have compared different types of house. So what you see here, there is a first category for detached house and the second one for row houses. Both of them are what we call single family house, and they represent 64% of houses in Luxembourg. And then the third category is multi-family houses, so apartments, and they represent 36% of houses in Luxembourg. We have also classified the houses depending on the year of construction. And what we see here is that the energy intensity is decreasing with recent buildings and also is lower for multi-family houses. So why? Because in both cases, we can avoid the heat losses because we have a better insulation usually in recent buildings, and we have also less exterior walls for multi-family houses. So of course, it's a general trend and you can have some exception. The variability of the data is quite large, but it's a general trend. So now let's look at dwelling size in Luxembourg. This is the data from Statec, where we see the average size for the three types of houses in Luxembourg. We can see that the average size is much higher in Luxembourg than the European average. This is the average occupation rate for the different types of house. This is aligned with the European average. So if we make the division, we can calculate the number of square meters per person for the three different types of houses. And before I speak about the last factor, which is the energy impact, I would like to open a new live poll because these energy impacts are influenced by how this energy is produced. And we wanted to know what is the energy source for your heating system. Is it gas, oil, electricity, wood, or others? So if you don't know, you cannot answer, but I would recommend you to get the information because you will have a better understanding on your impact and if you can find alternatives for your heating system. So I will let just a few seconds to be sure that everybody can answer. And we have time to consider all the answers. Okay, so maybe we have a sufficient number of people who answered. Yes, so if I read well, it's 63% of people using gas, and then just about 10% for the other oil, electricity, and wood heating. Okay, so let's see if it's aligned with the statistics in Luxembourg. We will go back to the presentation. So in Luxembourg, there are 35% of residents that use oil. And you see on this y-axis, this is the carbon footprint per kilowatt hour of heating. So the oil production generates about 320 grams of CO2 equivalent per kilowatt hour. Then the majority use gas as the participant of this webinar. And it has a bit lower carbon footprint, so about 260 grams of CO2 equivalent per kilowatt hour. Then only 5% use wood, and we can see here that the carbon footprint is much lower, about 50 grams of CO2 equivalent per kilowatt hour. So we are still emitting CO2 when we burn wood, but this CO2 was already present before the tree was grown for the wood production. So when the tree is growing, it is capturing CO2 from the atmosphere, and the same amount of CO2 will be released when we burn the wood for heating. So we are not adding any CO2 in the atmosphere, contrarily to fossil fuels. And then 4% use electric heating. So the carbon footprint here depends on how this electricity is produced, and we will see that later with Thomas. But in Luxembourg, there is still a significant share of fossil fuels, and that's why the carbon footprint is still a bit high. So are there other options than these four main heating sources in Luxembourg? The answer is yes. So we have put here the four results in terms of carbon footprint of the four energy we just mentioned. And we added three other energy sources, which are district heating, solar thermal, and the heat pump. And we see that the lower carbon footprint is when we use solar thermal energy to heat our house. So to put solar collector on your roof to heat your house. But to understand a bit the complexity of making decisions based on environmental criteria, we wanted to show you other indicators. The first one is the emission of particulate matter. So it's fine dust, so that is air pollution. And when we breathe this dust, it will irritate our lungs and provoke possibly respiratory disease. And we see here that wood heating, which was very good for the climate change indicator, is quite bad for the emission of particulate matter. So we cannot avoid the fact that when we are burning wood, we are emitting this fine dust. So either we should avoid to implement wood heating in cities to avoid to contaminate the health of the people living in the cities, or we should implement filters that can trap the dust in the chimney and avoid their release in the atmosphere. So this is an investment, but it can compensate this environmental trade-off. And finally, we wanted to show you another indicator, which is the use of mineral and metallic resources. And we see here that solar thermal energy, which was quite good for the two previous indicators, is now quite bad for this third indicator. So why? Because we need to build these solar collectors, and it requires several resources, and some of them are quite scarce, like copper or gold. So we really need to increase the recyclability of these materials to reduce this pressure on resources from the use of solar thermal energy. And now, if we look at the overall equation, we can calculate the carbon footprint for 1% for the different types of house. And as I said in the beginning, the average is 2,200 kilograms of CO2 equivalent per person per year, just for the use of heating. But there are very large variations. So you can have a footprint below 1,000 kilograms of CO2 equivalent if you live in a recent apartment, or above 4,000 kilograms of CO2 equivalent if you live in an old detached house. So of course, again, these are average data, but we can see that there is a very high variability in our heating impacts depending on the type of house we are living in. And to conclude this first part, we have seen that 60% of the emission from our house come from heating. So we can do something about this. We can try to reduce our use of heating by reducing the temperature, and also increase the efficiency of our house with small houses and efficient houses. We can also switch to low carbon alternatives, although we need to find solutions to avoid any trade-offs on other criteria. And with that, I will let the floor to Thomas to speak about electricity impacts.
Thank you, Laurie. It was fascinating. Now we will talk about the electricity consumption apart from heating. Just come down. Yeah. So electricity consumption at home. What do you think most electricity is used for? Well, we have some numbers. First, it's mostly actually TV and multimedia. Then it's refrigerators and freezers. Then it's lighting. And then it's mostly all the appliances we have, such as washing machine, clothes dryers, dishwasher, and other appliances, plus ICT equipment. So all the devices, specifically your Wi-Fi router as well, is included in there. So with all that, what can make the consumption vary? Well, first, it's quite simple. It's just the number of devices you have. The more devices you actually own and charge and use, the more your consumption. So it's good to always adapt your purchase to the real needs. Then the time of use is quite important. If you just let your devices plug all the time, even standby, it's still a bit of consumption. So turn it off if it's in use. And there's also some eco-friendly behaviors we can recommend. I know I excluded the heating in here, but still temperature settings are quite important. And make sure you have well-maintained appliances, such as water heaters could be a huge consumption. And with all that, you could actually have 10 to 40% savings just through eco behaviors. So it's actually quite significant. But of course, it's not only about that. This is more or less things you could do overnight, just behavioral, just change you can implement right now. With a little bit of investment, you can also actually change your device power just by changing the device, actually. So there are energy labels that are mandatory for 14 product types in the EU. You're probably very familiar with it. It ranks from A to G. Now there's also A+, A++, and A+++. That gives you the consumption per year in kilowatt hours per year. So you may have an idea of how much you will actually pay just to have this device running over the year if you know the price of the kilowatt hour. And there's a lot of other information depending on the type of appliance. And with that, it's actually quite significant what you can get. You can decrease your consumption, by 20 to 70% with the best class devices. So it's actually worth it, and you may save money on the long run, on top of saving emissions, of course. I believe there's a poll now, because we will talk about the other side of electricity, which is not consumption anymore, but production. And since it's quite important to know about what electricity you consume, we would like first to check if you have an idea here. What is the correct ranking of electricity sources from the highest to the lowest carbon footprint? So you start with what emits the most and ends what emits the less. So is it 1, gas, coal, solar, and nuclear power? Is it coal, gas, nuclear, and solar power? Is it gas, coal, nuclear, and solar power? Or is it coal, gas, solar, and nuclear power? I can leave you a bit of time. So we want to know over the life cycle, of course, just not direct emissions. And we include other gases than CO2, so it's CO2 equivalents, meaning methane, for example, is part of it. Okay, maybe 5 to 10 seconds. Good, let's see. So most of you, actually half of you, answered coal, gas, solar, and nuclear, then coal, gas, nuclear, and solar, and then a minority answered with gas first. So that's actually a pretty good guess. Let's go to the next slide. And the answer. So here's your portfolio of electricity technologies. You have to remember that a lot of these numbers may actually change. This is actually on the higher side of what you can find, because here we include, of course, the life cycle emissions, the non-CO2 emissions, which is quite important for the fossil sources, because you have fugitive emissions of methane, mostly for coal and gas, at extraction. So that also contributes to climate change, of course, before you even burn the fuel. So coal, oil, and gas are the trio of fossil fuels. Gas actually can reach quite low numbers here. Sometimes you see numbers such as 400, 450 if you manage to avoid these fugitive methane emissions, but it's quite uncertain. Then biomass, also another combustion technology, but of course, as Eloise said, we don't account for the CO2 that's emitted then because it's considered part of the natural carbon cycle. And then on the right side, you have the non-combustion emissions, starting with nuclear power at 18 grams. So it's mostly from constructing the plants and the supply chain of the feedstock of uranium. And then hydropower, wind onshore, wind offshore, and solar power. Wind offshore has much higher capacities than wind onshore today. So that's why if you make bigger wind turbines, you have a lower number. Solar power still has a bit high. So today we see between 50 and 70 grams per kilowatt hour, but it really depends where you are. If you're in a very sunny place, this number can decrease quite much. And also if you manage to build your solar panels with low carbon electricity, this will also be reduced. So don't take these numbers for granted. It's just to give you an order of magnitude. And if we take everything into account here and use the LCA database Eco-Invent 3.6, we find that Luxembourg has about 450, 460 grams per kilowatt hour. That is if you don't choose your electricity, which will be the object of next slide. Yes, and of course the answer to make sure we were right. So 50% of you were actually right in this ranking. So of course, all these technologies don't run all the time at the same pace. They don't all produce electricity concomitantly. So one specific property of electricity is the difficulty to store it. So because of that, it needs to be produced when it's consumed. But it's not always easy, right, to match consumption. So depending on load, which is the aggregate final demand, on climate, on trade with also neighboring countries that might exchange electricity with you, or maintenance of power plants. Some of them have to be closed for maintenance. The mix can change even every hour. So here is just for the same day of December 15, I think, yes. So a common winter day in France, Germany, and Belgium. Unfortunately, we didn't have the data for Luxembourg. This is from, by the way, a fascinating website called electricitymap.org, where you can actually check the live production of electricity in different countries. And you can see, so I used the same color code as this figure earlier, but you can probably guess what these different technologies are if you're a bit familiar with the topic. But for example, France uses a lot of nuclear and then a bit of wind and hydro and gas on top. In Germany, it's more a mix of coal and wind power. There's a bit of sun here, but it's a winter day, so of course it doesn't. You would just see a summer day, which I didn't have at the time, but it's actually quite impressive. And a bit of gas on top. And Belgium is a bit in between with nuclear, wind, and gas. So of course, there's also exchanges of electricity all the time between the countries. But during a same day, just to show that the carbon intensity of electricity can vary. For example, France between 50 and 80 grams CO2 per kilowatt hour, in Germany between 250 and 380, and Belgium between 150 and 250. So it's quite difficult to understand what to do with this information because for now, well, what does it mean that I should plug actually my appliances when it's the lowest? What do I do, especially in Luxembourg where we don't have this information? Well, you can first choose to do nothing and use the consumption mix of the country. So this is the Luxembourg consumption mix based on the domestic production. So that's probably where you can see, yeah, that's where you can see most of the wind and biomass actually, mostly in Luxembourg. And then because we're really well connected with Belgium and France that still have nuclear and Germany that still have coal, we still have a share of nuclear and coal in the mix, in the, let's say, average mix, consumption mix of the country. But of course, you can choose to do something else. You can choose a green electricity contract. For example, we picked the ones at Enovos here, but a lot of them are actually available on the market. And Enovos proposes two contracts. So there's the one called Naturstrom, which relies on a scheme called Guarantees of Origin, which specifies, so which states that somewhere in Europe there has been the same amount of electricity you consume that has been produced by renewable electricity. So here it's mostly hydropower. It's actually 100% hydropower for Naturstrom from Scandinavia. All in all, if you look at the Institut Luxembourgeois de Régulation report, you will find that, for example, 20% of electricity was produced in Iceland. But of course, you may wonder why Iceland is here, since Iceland is not connected to the network. And that's where Nova Naturstrom can help. Let's say that the first contract is actually something that's valid, that's legal, that you can use. But if you want to be more, to have an influence on the mix, you can use Nova Naturstrom, which restricts these guarantees to the national and regional renewable energy sources and the newer power plants. So you would have a better effect, let's say, on the grid. And since it's not only Enovos, you can go and visit this really nice website called calculix.lu that will give you the full list of different contracts you can choose. If you're more into wind, or if you're more into hydropower or anything, you can actually have quite a detailed information in there. Just about the flags here, it's just representative. It's not exactly the geographical representation, origin, sorry, of the electricity. But if you're interested, we can probably look a bit more into detail. And then we couldn't close this without speaking about smart houses. So on the consumption side again, so we went consumption, production, consumption. The concept of smart house has emerged. So to cover aspects such as energy efficiency, but also assisted living, healthcare, comfort, convenience, safety, and security. So the concept really relies on the idea of that your house could actually be equipped with a lot of sensors and devices that would detect when and where to use energy the most efficiently. But again, since we work with life cycle assessment, the question we have is, we need to make sure that such a system makes sense, namely the benefits from energy saving higher than the impacts of connected objects and their use. So for example, for the latter, on the left-hand side, we have to consider the additional energy consumption of sensors, the connected objects, and the data transmission. We also have to check whether these sensors don't contain too much of critical materials in the devices, and check that the currently low recycling rate of electronic waste is not an issue. Of course, the recycling schemes usually tend to grow in volume and tend to be economy efficient, cost efficient, when there's a certain volume of the device and materials. So we can't really say now if it's a good thing or not. On the other hand, are devices also running as intended? Are there any routine effects? So for example, some of the devices might be very interesting for the first 3-4 months, and then we kind of forget about it. That's actually some behavior that has been documented in the couple of papers we see on the right here. Yeah, and so in the end, smart features might not even be fully used. So you might spend money and energy into having sensors that are not used. So there's this whole question of, is this adapted to their use? Of course, for people who actually use the smart house as it should be used, it's probably very efficient, but we also have to ask these questions. Okay, bit of a conclusion here. Yes. So some takeaway messages from this section. Eco-friendly behaviors can definitely reduce the impacts of energy and water use. That's pretty clear. But of course, you decide what level you want to adopt. So do you actually want to cut all the heating at your home and live with 2 sweaters all the time? That's your decision. But of course, you can always find a in between. The use of electricity and water can be significantly reduced as well with eco behaviors. We didn't talk about this. And finally, electricity green contracts covering, especially the ones covering low carbon recent power plants, could facilitate the energy transition. Some of them are not so efficient to drive the energy transition, so you may want to actually look which kind of energy are paid by your money if you choose these contracts. Okay, I will leave the floor now to Melanie for a bit of house design.
Thank you, Thomas. So indeed, now we are going to look at the contribution of construction materials to housing environmental impacts, and especially focusing on their carbon footprint. First of all, the slide pass. Yes. If we look at the major part of the existing building stock, it's made of buildings constructed before standards were requiring some thermal performance for the building. And the carbon footprint induced by the manufacturing of materials represents around 20% of the carbon footprint arising from the whole building life cycle. This corresponds to the embodied greenhouse gas emissions, and this is what you can see in the blue bar on the graph. So this means that the greenhouse gases emissions which arise from the energy used during the use phase of the building represent more or less 80% of the building carbon footprint. And this is represented in green on the graph, and it's called operational greenhouse gas emissions. What is interesting to understand is that the new standards for building construction require some strong operational energy performances, and so it reduces the corresponding share of operational greenhouse gas emissions in the building carbon footprint, and so it makes the contribution of the embodied greenhouse gases more significant. So you can see, for instance, in the bar in the middle of the graph, the embodied greenhouse gas emissions represent 35% of the total building carbon footprint as an average. And this contribution also increase even more if we consider the standards, the advanced standards for the construction of passive houses or net zero energy buildings, for instance. So you can see here on the last bar that in average, the contribution of embodied greenhouse gases emissions can go up to 50% of the full building carbon footprint. So this means that it will make more and more sense to care about the choice of materials if we really want to reduce housing carbon footprint. So to deepen this issue, I would like to ask you a question, so we can go to the poll. So according to you, what is the correct ranking of building materials from the highest to the lowest carbon footprint? Is it concrete, then steel, then wood? Or is it steel followed by concrete and wood? Or is it steel followed by wood and then concrete? So if you know, please vote. And if you are not sure, just try vote as well, and we will see what is the correct answer just after. So we will wait a few seconds to leave you time to think and vote. And we will continue. Are we okay? Do we have enough answer to continue? Okay, so more than 50% answered steel, which is the most impacting, then concrete, and then wood. And yeah, also a lot of you answered concrete, steel, and wood. So this is in line with the trend that we will see now. If we can come back to the slide. So yeah, the correct answer is steel and concrete, which have higher carbon footprint than wood building frame. This answer is based on the study from Sad and colleagues, who made an analysis of existing studies comparing the impact of wood versus concrete building frame, wood versus steel building frames, and concrete versus steel building frames. And so based on the results of this analysis, almost all studies comparing wood with concrete or steel building frames concluded that wood is the best options in terms of greenhouse gas emissions. And conclusions on studies comparing steel and concrete building frames are more moderate. So we can say that these two materials remain comparable in terms of greenhouse gas emissions. So why do we have these results? Steel has the advantage of being fully recyclable after its use, but the process of recycling is energy intensive, and so it induces some significant amounts of greenhouse gas emissions which are released into air. So it explained the high carbon footprint. Then if we look at concrete, so generally concrete is produced locally, but its production induces significant airborne greenhouse gas emissions as well, especially due to clinker production, which is an ingredient of the cement. And also concrete is a heavy material, so it means that it will induce additional impacts for its transport, even if it's usually produced locally, as I was saying before. And also regarding its end of life, the options for its valorization are really limited, so it contributes to the carbon footprint. And this is also a real problem for a country like Luxembourg, where place is lacking for the landfill of these materials. And so if we look at wood, so wood is generally a local material and it's renewable. And as Eloise said before, it's able to store some carbon dioxide, so it delays the emission into the atmosphere. It's also a lightweight materials comparing with concrete and steel. But wood has also some environmental drawbacks. It's induced to consume more land, to use more land for the growing of trees, and it can induce also potential impacts on biodiversity. Also, wood products used in construction generally receive chemical treatments to protect them to protect wood from fire or deterioration, and so these chemicals induce some impacts, and they also limit the option for the valorization of wood after use. So, of course, these results are valid for the carbon footprint, but if we would look at other types of impacts, the trends could be different. Now, if we look at single-family house embodied greenhouse gas emissions in more details, we can see that whatever is the materials for the building frame, the walls remain the main contributor to the greenhouse gas emissions. So now I would like to highlight some trends on impacts from walls, focusing on the manufacturing of structural and insulation materials, which enter the composition of walls. So I took as a reference 1 square meter of wall of a single family house, quantifying the amount of the various structural materials based on a study list made a few years ago for the Fonds du Logement. So in green, you can see the amount of each materials that would be required for 1 square meter of wall. And in blue, you can see the corresponding amount of greenhouse gas emissions, which are induced by the manufacturing of each material. So we can see that there is no correlation between the weight of materials required for 1 square meter and the impact of their manufacturing. But we can see that materials from natural origin or materials requiring very few intermediary or transformation steps are less impacting. If we look, for instance, at the wood products, we have massive wood that has been considered untreated and glued laminated timber. We can see that this one, glued laminated timber, has a higher impact than the production of massive wood. This is because there are more steps that are required and to make the wood pieces at the right size, for instance, and also it induced the use of glue for the assembly of the different work pieces. So that's why we have a higher impact than for the massive wood, for instance. On the same way, we can also compare the greenhouse gas emissions induced by the production of insulation materials. So here, for each of the 7 materials that are compared, the quantity required for 1 square meter has been calculated considering an equivalent thermal resistance and the intrinsic thermal conductivity of each material. The thermal conductivity, it represents the ability of the material to conduct heat. And so what we can see on the graph is that materials required with the lower quantity induce the most significant amount of greenhouse gas emissions during their manufacturing. And this is due to the fact that these materials are fossil-based materials. And so it induces large amounts of greenhouse gas emissions. And once again, what we see is that materials that are made from natural or renewable sources induce the lowest impacts on greenhouse gases. Of course, once again, if we look at other impact categories like land use or water use, the trend would be different, and probably that bio-based material would have a more significant impact for these categories. And finally, for the comparison of materials, if we now look at the carbon footprint of the complete wall composition, so still considering 1 square meter of a single family house, we see that structural material, whatever it is, represents the major part of the wall mass. But on the other side, it's not the main contributor to the carbon footprint. And if we look at insulation materials, they are not really significant in the mass. It's represented with the red bar here for the mass, but they induce strong variations in the carbon footprint, as we can see with the red bar in the carbon footprint result graph. So if we look at these results, stone combined with wood wool appear as the best combination. As I showed before on the previous slides, the other materials required more transformation steps, and so it induced more energy and substances consumption, so there is a higher amount of greenhouse gas emissions released into air. So of course, these results, they remain illustrative and they must be understood as trends. In order to be fully representative, they should be adapted to each specific building, also including beams and other framing elements. And the combination of the thermal resistance of each wall component should be considered in the calculation, not only the one from insulation, as it was the case in these examples. But at least it gives an overview of the trend of the carbon footprint of different construction materials. So to close this part on house design, I would like to say a few words on the advantages and inconvenience of building a new house compared to renovate an existing one. I will not give too much details because there are a lot of different parameters that would influence the environmental advantages. But what we can highlight is, of course, that renovation would allow to improve the thermal performances of the building. And we can go up to reach the performances of a new built passive house. So if we consider equivalent thermal performance for a renovated building or a new building, renovation, of course, will induce limited intensive use of materials, and the new construction will induce a higher amount of materials consumptions and also additional land use. So this overview gives a small advantage for the renovation in terms of carbon footprints, but this trend could eventually be moderate if materials with high embodied greenhouse gases are chosen for the renovation, or if some additional surface of living is created with the renovation, for instance. And now I come to the take-home message for this part on house design. So we saw that the building materials represent 10 to 20% of the housing impact for the most part of the existing building. But with the new standards and the new thermal performances expected for new building, this part could increase. Then we saw that there are some environmental trade-offs depending on the impact categories we consider between bio-based and mineral or fossil-based materials. And we just saw that renovation of non-efficient buildings can lead to significant materials and energy savings, but this can be influenced with the choice of materials and many other parameters. And so now I leave the floor to Elohi for the final conclusion.
Yes, thank you, Melanie. Now I will conclude this presentation, and to do that, I wanted to give you some tips for you to decrease your environmental impacts of your house and your housing habits. So the first category we show here is the quick wins. So it's a new behavior you should implement. Normally, it's easy to do it once or twice, but the difficulty is to really adopt this behavior in a systematic way and on the long term. So this is not an exhaustive list, of course, but we mention here the low temperature settings, both for heatings, but also for the water and so on. Short showers, so avoid the bath. Also, it's important to turn off equipment and not let them in standby, and also unplug them, because the computer still consumes electricity when it's turned off and plugged. Also, try to favor eco program for your dishwasher or your washing machine. Have a good maintenance of your equipment will favor the savings in terms of energy and water. We have seen with TOMA that normally the carbon footprint of our electricity is lower during off-peak hours. So if you can, of course, try to do your washing machine during the night, but I know it's not always easy. And we have also seen the advantage of switching to a green contract, in particular the one that invests in recent renewable energy plants that can foster the energy transition in Luxembourg or the greater region. Then if you want to invest a bit of money, you can try to replace your old equipment and buying efficient equipment. For example, with the energy label, you can choose A label equipment. So maybe it will be a bit more expensive, but to compensate this, you can go for smaller size equipment that can be cheaper and that will consume less than large size equipment. Also, to change your bulbs to LED lighting should be quite easy. And if you want to invest more effort, you can also install low carbon heating, but for that you will need to get support from specific experts and consultants. You can also ask for subsidies from the government. And for the last category, so if you want to make really big change, you can try to refurbish your house. Again, you will need some support, so you can ask in Luxembourg, for example, myenergy.lu or energieagence.lu, who will make a diagnostic to see where your building is non-efficient and how you can best refurbish it. And if you want to make a life change, you want to move, so try to move to a smaller house. We have seen that in Luxembourg the houses are quite big, and to a passive house, or if it's not efficient, to refurbish also this new house. If you move to a house closer to your work, it will also decrease your mobility impacts we have seen in the previous events. So it's really important to implement all these steps, all these new behaviors at large scale, because we need to change the trend in Luxembourg. So the energy consumption of households in Luxembourg is still increasing. So this is the comparison between the year 2000 and 2017. And we see that it's increasing. This is due mainly because we are building more dwellings, so there is an increase of population in Luxembourg, but also we are building larger homes than before. So we really need to change this trend, and for that we need to increase the green bar here, which is energy saving. So we need to implement as much as possible energy saving to compensate this increase of population and decrease the energy consumption and therefore the impacts of housing in Luxembourg. So with that, I will finish the presentation. I hope you enjoyed, and we can move to the question and answer session. So I have seen that some of you already wrote question. I will just open the chat. So we will start with the first presentation. We'll go into the order to facilitate. So the first question is from Joy Mengen. Why is the temperature rise higher on land than on sea? So maybe Thomas, since you mentioned this, you can try to answer.
I can take that. So the answer is quite simple. Water has a better heat capacity than land. So the transfer of heat from air to water is much more efficient than the transfer from air to land, meaning that air over water will actually be a bit colder than air over land. So on average, we have, I think, 1.2, 1.3 warming, but over sea it's 1.0, and over land it's 1.9. It's not always true. For example, in the Arctic, so the Arctic warms much faster than the rest of the globe. So it's sea, but it still warms. So it's not a systematic rule, but overall it's because heat is better at absorbing heat. Water is better at absorbing heat.
Okay. So unfortunately, we cannot see you and we cannot exchange directly with you. But if you're not happy with the answer that we give, just write another question, and you can also write to us directly via email after. So it's a bit unfortunate that we cannot exchange directly. We hoped we could do it before the pandemics, but now it's this situation with the webinar. Okay, so the next question is how much household water use per person per year on European level? So in fact, I didn't specify this, but the figure of 150 cubic meter of water per person per year is a European average. So there are less variation between countries for water use, and we don't have specific data for Luxembourg. That's why we use the European average. We have much more data on energy use at the national level, but not really for the water use. But we expect that the variation between countries are less significant than for energy use. So I will take the next question. So fossil energy sources did also capture CO2 in the past, or do I am wrong? No. So yeah, it's a CO2 that is in the ground, but I don't know, the time frame is thousands and thousands of years. Or Thomas, can you specify?
Yeah, it's hundreds of millions of years, actually. Yeah.
Yes, exactly.
So we don't consider it renewable at this scale. It's too high.
Yeah, so exactly. So now what we are, the climate change we are feeling now is due to this additional fossil CO2 emission we are adding in the atmosphere. And it's not from the natural cycle on a very much short term due to, for example, the wood combustion. Also, we also have a CO2 due to deforestation, like Thomas said, but it's not the same time range. Okay, we have a question from Frédéric Conrad. Why does heat pump emit 50 grams of CO2 equivalent per megajoule? So this was based on a database called EcoInvent, and the heat pump works like a reverse fridge. So either you capture the heat from the exterior air or from the geothermal energy. We have made a mix of the two types of technology, and we still need some refrigerant and electricity to make it function. And so the heat pump impacts will largely depend on the impact of the electricity to run the heat pump. And here we use, again, the carbon footprint of the electricity mix in Luxembourg, and we obtain this 50 grams. So, for example, if you supply the heat pump with a low carbon electricity, you will get much lower impact. And on the contrary, if you feed the heat pump with coal energy, for example, you will obtain a much higher carbon footprint. So it really depends on this electricity amount. So I hope anyone can want to add something about this number, or is it clear? It's a bit frustrating. We don't have So what is the correct ranking of electricity sources from the highest to the lowest carbon footprint? So this is the question we asked. What is the answer to this question regarding the emissions during the use and not during the production? So Thomas, you want to answer this question maybe?
The ranking would be the same in direct emissions. So coal would be between 1,000 and 1,200 grams per kilowatt hour, depending on the quality and whether it's hard coal or lignite. Then gas would be about 400, and the two others actually don't emit CO2 on site. For nuclear, you would have the supply chain, so I don't know if you want to account that for direct, but the ranking would be more or less the same. Would be the same. So.
Linked to that, we have another question about the energy production. So could we theoretically produce enough energy from renewable sources situated here in Luxembourg for all the people in Luxembourg? So Thomas, I will let you again speak about that.
Yeah, no, it's a really difficult question. The key phrase is for all the people in Luxembourg here, knowing that we will be more and more and that our consumption patterns are really high. it's currently hard to imagine that Luxembourg would be self-sufficient in, at least in electricity production, and let alone in energy. So remember that electricity is only a part. It's probably I don't know, 20% in Luxembourg, and 80% is just all the fossil fuels we use for heating and driving. And this is even harder to for example, to get. It's harder to electrify and to make it renewable, because you first have to change also the whole structure of the consumption. I think there's been just calculations to understand how much space you would need to produce the energy that Luxembourgers are using, and I think it's quite significant in terms of the size of the country. But I don't want to give any number now because I don't really have them in mind. So the question is that it would be really hard. The answer is it would be really hard.
Yeah. Okay. The next question will be for Melanie, I think. So in the comparison made between different insulation materials, was the issue of thermal bridge taken into account? In other words, is it possible to ensure no thermal bridges in a house in stone? Considering materials in isolation might lead to a biased conclusion, isn't it?
Yeah, so indeed, the example I gave, it's really related to the impacts from the materials production. And as I mentioned, this is the results I presented are really illustrative and to be really representative of a real building. The whole configuration of the building should be taken into account, including thermal bridges and the different type of windows, doors, their dimensions. So everything should be dimensioned really specifically to each building. That's why there are some studies made before any construction, and then based on the specificities of each building, we can choose the insulation material that would fit the best, what would be the best option for the insulation materials. But yeah, the results that I showed here was really aiming at showing the variations of impacts from the materials production, manufacturing phase.
Yeah, we will need a full study to understand all of this,
yeah.
And we wanted to provide a simplified approach to have some elements of understanding. So the next question is about eco-programs. I understand that eco-programs are saving energy, but are they also eco-friendly regarding other resources like water? I mean, seen all together, are eco-programs the best option to use? So they first focus on energy saving, but I think they also can, depending on which eco-programs, save water. But even if they do not save water, we have seen that for example, in terms of carbon footprint, the impacts due to the production of energy in terms of heating or electricity is much more impacting than the production of water. Then maybe you can have a question about the water stress. So the fact that we are using water and it has an impact on the water resources. But in fact, here we are not losing water when we are using our equipment, only a bit of water because, for example, for a washing machine, there will be a small percentage of water which stays on our clothes. But most of the water return back to the water resources. So it's, let's say, smaller issues than the energy usage of our equipment. So it's still good, and I think there are also some studies about the environmental impacts of this eco-program that show that they can bring benefits without any trade-off. So the next question is about air conditioning. So what about air conditioning and the impact of not just the energy use of air conditioners, but also the manufacturing of refrigeration technologies? Yeah. Thomas or Melanie, one of you want to take this question, or should we didn't speak much about air conditioning because in Luxembourg there is almost no air conditioning for residential buildings. Now there are more and more air conditioning installed in the southern country of France and in the in the southern country of Europe, and also now in the middle part of Europe a bit, because we have some very hot events in summer. But of course it has a huge impact because first the production of this technology, and also the fact that if you have any leakage, then the refrigerants have a very high global warming potential, as Thomas shown. So these other greenhouse gases that he showed at the beginning, there are very small amounts emitted today in our society. But if we emit them, so if we have a leakage in the system, then they are very powerful and they create a very large impact on climate change. So I am not sure what is the proportion between the impacts of the use and the production of air conditioners, but I don't know if you have an idea, the proportion between the two.
I would say that regarding the use, it induced an electricity consumption as well. So
Yes.
Looking at the full life of the building, I mean, if we use it for, I don't know, maybe, I don't know what would be the lifetime for air conditioner, maybe 20 to 30 years. If we look at the electricity consumption during this period compared to the greenhouse gas of the production of the system itself, I think the use is providing a higher carbon footprint than the production of the air conditioner. But then, I don't know, compared to the heating system and the heating energy consumption, I'm not sure of if it's bigger or lower than this.
Yeah, sorry, we didn't investigate too much this question because it was not really common in Luxembourg. But yeah, we could do it in the future. So there is a comment from Franminet. In Luxembourg, it makes no sense to heat the house by solar thermal energy. You would need too much panels in winter time to reach the energy demand, and in summer you can store it. Solar thermal energy used in Luxembourg for heating drinking water and can help at a very small part for the central heating. Yes, so we didn't say that to install solar thermal energy, we just wanted to compare different alternatives to heat, and this is why at the end I said that if you want to switch your heating system, you need to get advice from real experts that will guide you. So yeah, it was not our intention to say to install solar thermal, it was just to compare for the same amount of energy, different sources of energy for heating and see what are the environmental advantages or drawbacks of these different modes of production. Do you want to comment, Melanie or Thomas, on this? But of course, it makes more sense in a southern country, and we agree with you, Frank. So other places, countries or city where the size of housing square meter per person is limited in new construction. The size of, so like the regulation will put a threshold that we cannot overpass for the new construction in terms of square meter per person. I'm not aware. Are you aware, Melanie or Thomas?
No, it's a really good question.
Yeah, it's a good question. I'm not sure, but I think in big city like Singapore or New York or any big cities, maybe there are some limitations, but I'm really not sure. But I think it would not be related to environmental purpose first. It would be a matter of places, I mean, of space to build some new housing.
Because I think there are only 2 questions left. I will just ask them quickly. Will hydrogen be the ultimate solution to solve the crisis? And I think this is a question that Thomas can answer because he studied the problem of hydrogen.
One thing we have to remember with hydrogen is that it doesn't exist in nature. So you always have to produce it by something else. Right now it's produced mostly through natural gas. We want to produce it through electricity because then it would allow us to actually make decarbonized hydrogen. But it will take some time before it's completely deployed. And in the meantime, we'll keep using hydrogen from fossil fuels. So on the production side, it's already quite limited, but on the consumption side, if we're thinking about using hydrogen for heating or for driving, for example, it also means that we need to change the whole fleet of devices. Transportation of hydrogen also is actually quite complicated. Hydrogen is the smallest of all the atoms, so there's problems of diffusivity in the networks. So there's a lot of technical challenges. Doesn't mean that it's not possible, but it also means that if we want it to solve the crisis, as you say, which I think it means to decarbonize or to limit climate change, it would need to be produced from a large amount of renewable electricity, which for now is not quite easy to have. So we first need to decarbonize the grid, and then probably we can get on with the green hydrogen. But we still need to get it from somewhere, and actually the production process is not so efficient right now. There's of course other small, at least lab level production processes that are imagined. For example, at LIST, we have a few projects on producing hydrogen from photosynthesis, photolysis, which could be an option. But of course, all of that is very, let's say, medium term, and we need solutions quite fast. So there's a lot of questions around the temporality of this deployment.
Okay, and maybe we continue with the last question, which is a bit similar. So it's still Sandra Selina who asks, are there places where there is a bathtub or private swimming pool ban? And again, I'm not sure about this. I heard that there are some restrictions, for example, in Las Vegas, where they had a very water crisis due to the fact that they are in a desert with a lot of water used for their pools and so on. But yeah, specifically, I don't know if you have some other inputs, but I'm not sure.
No, I don't know.
Yeah. But it's true that for now, the limits are more to ensure the comfort of people, so to have minimum size of houses for the person than to put restriction on the superfluous comforts. So with the bath ban or swimming pool ban or a maximum size for her house. And yes, I don't know if this would be acceptable, but at least we need to rethink our way, how we live in our house and how we consume energy and water in our house. So I think we can conclude the presentation with this. I would really like to thank you for staying at this webinar until now, and I will just take the opportunity to announce our next event on the impacts of food, which will be on the 18th of March, again with a webinar. So if you want, you can register. You can go to the website of LIST and register to this next event in 2 months. So thank you very much again, and I hope I see you for the next event.
Thank you.
Thank you. Bye-bye.
Bye.